Okay, hi everyone. So I wanted to try and talk a little bit about computation, how to do it, kind of how to get a computer to do really cool and powerful things, kind of how to take sort of the latest AI kinds of technology and make it do what you want it to do. And I've spent a really long time, actually close to 40 years now, developing technology to make all this easy. We have this thing called Wolfram language, which is also what's inside this thing called Mathematica, that gets used by lots of people in the world, lots of most universities, lots of people in research and development, lots of people doing all kinds of fancy science and so on, plus lots of kids. And so what I wanted to do today was try and give a bit of an introduction to computation using the language that I spent many years building to show you how you can get computers to do what you want. And we'll talk a bit about graphics. We'll talk about things about data about the world and geography. We'll probably talk about machine learning. Talk about a bunch of things. Now the real question is, am I going to be able to get people to follow along and actually compute with me? And I don't know whether this is going to work because I'm not sure exactly how everybody is set up. But if you have a web browser, you should be able to go to our Wolfram Cloud. You should be able to get a cloud basic account if you don't have other access. And then you should be able to follow along with what we're doing. But we're going to find out how many people can do that. And if not enough people can do that, I will show you a bunch of stuff, and then you can separately offline be doing things for yourselves. So let me go ahead. I can get started here and just show you a few things. So we got okay, so some people are saying yes, some people are saying no. All right, the trickiest situation, of course. Okay, guys, you're making it hard for me, but that's okay. All right, let me share my screen here. So, and I should say that if you have access to a desktop version of Wolfram language through Mathematica, for example, that will all work just fine as well. Okay, if everything works perfectly, then you should have something that looks, you should eventually have a screen that looks something a bit like this. This is what we call a notebook. It's the thing you use to communicate with the machine, and you type things into it. So for example, we could type in 2 plus 2. And if it gets this wrong, it's going to be really embarrassing. But the idea is type that in, and then when you want to get the computer to compute something from it, you press Shift-Enter. It means you hold down the Shift key, you press the Enter key. Boom. Okay, says 4. Good sign. So my question here is, how many people are able to follow along with that, and how many people cannot? If you can, let's just see whether we're getting results here from the poll. Well, I'm going to assume you can follow along for now, okay? And I also would like to know a little bit about what your level of knowledge of different things is, but we'll get to that. Okay. Okay. All right. I'll tell you what. Let's okay, great. People saying it works. That's a very good sign. All right. So how about you can type in let's do something where you make a bigger number. Let's say you type, if you know about powers of numbers. Well, actually, we could just say, you could just type in 2 times, you type a star, times 2, times 2, times 2, times 2. You'll get that. Math thing, if you don't know it, instead of typing all those times 2, times 2, times 2, you can say 2 to the power with a wedge, and you just say how many 2's you want to put in. So this would be 2 to the power 5, and the answer to that is 32. But I could perfectly well say here 2 to the power 100, and then I'll get a much bigger answer. Or maybe I could say, let's see if I live really dangerously here, I could say 2 to the power 1,000, and I'll get an even bigger answer. Don't go too far if you're running it in a web browser in the cloud, because that's using shared computer resources. If you were doing it in your own computer, like I'm doing this on my own computer, I'm going to try 2 to the power, let's try 100,000. Oh, okay, that worked nicely. So there's the result, very big number. So we're making the computer do a bit of work for us here. Okay, so, but anyway, let's come back here again. So make sure you know how to do this. You type in a question, like let's say 3 to the power 10, and to get the computer to answer, you press Shift, hold down Shift, press Enter, get a result. Okay, is this working for people? I hope so. Okay, all right. So a lot of the way that things are set up is by telling the computer different functions we want it to run. So the way that works is you would say things like you give the name of the function. So for example, one function is range. And the way you type in these names, and there are just a few things that you really have to learn. So one of them is to type in the name of a function, every word in the function starts with a capital letter. Okay, so you type in range with a capital R, and you'll see an autocomplete, so you don't actually have to type all the letters. But okay, and then type a square bracket, open square bracket. That's on the right-hand side of the keyboard. You're going to say range, and then open square bracket, type in 10, for example, then close square bracket. Okay, so then press Shift Enter. So what does this do? This, you told the computer to make a range of numbers from, in this case, from 1 to 10. Okay, so see if you can do that. You can always go back and edit what you already did. So you can like change range of 10 to range of 20. And then when you've made the edit, you press Shift Enter and you'll get a new answer. Or we could say something like, let's say range of 50 here. Okay, so that will get the answer. People get it? Okay, so like, for example, we could say, if we wanted to, we could say range of 50, and we could say we want to take that sequence of numbers from 1 to 50, and we want to say, let's take that to the power 3, for example. Okay, so we just say range of 50, we edit after that, we say wedge 3, press Shift Enter, and we'll get a result. So those are the, if you're into that kind of math, those are the cubes of the first 50 numbers. Okay, so that's a bunch of numbers. Let's say we want to make a picture based on those numbers. All right, so we go in and edit here, and where we edit, click just like you would edit anywhere else. You just click before that thing and you start typing. So I'm going to type list plot and then a square bracket. List plot with a capital L and a capital P, and then a square bracket, because it's a function too. And then you're going to, at the end, you're going to close the square bracket, and that's going to say, make a list plot of range of 50 to the power 3. Okay, so let's see what that does. See what, I'm going to wait so that people can do it before I do it. So if you manage to get that to work, that made a plot. So that's showing, this is a graph where we're showing each successive value, we're showing it plotted on a graph here. Okay. So we can do all kinds of things like this. I wonder what we should do next to just get people familiar with what's possible. Let's try, okay, I've got another idea for what we can do. So let's go kind of, let me show you how something else works. It's another function, it's called table, and it makes tables of things. Okay, so we can say, and this is getting a little bit trickier, but shouldn't be too bad. let's say, so we're using, again, this power thing. And now this is where it gets, this is probably the most conceptually complicated thing we'll talk about, because once you understand this, there's lots of stuff you can do. So let me show you, what's a good way to do this? Yeah, I think this will work okay. All right, I'm going to show, actually, I'll tell you what, let's just start off by saying table n, and then we're going to put a brace bracket, which is a shift of the square bracket, n, comma, 10 here. Okay, so what is this doing? This is saying make a table, and what's in the table is just this thing we're calling n, and this is saying, well, let me just show you what it does. This says make a table of n with n going up to 10. So that's what we get. We can edit this. Let's say we put n wedge 2 here. That's going to make a table of successive powers of 2. So, I'm sorry, successive squares. So it says make a table of n squared, n going up to 10. Okay? Okay, there's a trick that's worth knowing. If you type, like on a Mac, it's Command L, on a PC, it's Control L, Command L, it will just make a copy of the input that you had above. Let's make a copy down below so it's easier to edit. Okay, so let's try, instead of putting n squared here, let's put a completely different kind of function here. Let's put in something that says, how about we put in Roman numeral? Okay, so this is let's say Roman numeral of n. So what's this going to do? This is going to give us, so hopefully you guys aren't all too modern to have ever even heard of Roman numerals. But we could use something different here, but I thought this would be kind of fun. So Roman numerals are just a different way to write numbers, but they have the, we could, for example, say, let's make the first 100 Roman numerals. Okay, so this is going to show the numbers from 1 to 100 written out in Roman numeral form. Okay, so one of the things about Roman numerals is they had a different way to specify numbers, like 1 was just an I, 2 was I, and then 10 was just an X, and by the time you get to 100, it's just a C. So a question is, was it more efficient to write things out in Roman numerals, or more efficient to write things out in our current numbering system? And so one thing we could try to work out is what's the length of the numbers in Roman numerals as compared to the length of numbers in our number system. Okay, so people are managing to get this to come out. We can make an edit here. We can say, instead of Roman numeral, let's say how long were those strings. So there's a thing called string length that will, again, put square brackets around it, because it says, it's saying what's the string length of the Roman numeral of n, with n going up to 100, make a table of those things. Does that make sense to people? So we're kind of we're just telling the computer what we want it to do. We have to use this kind of precise language so the computer knows exactly what we mean. But now we can go ahead and say this. And now it's going to tell us, so that's going to give us the length in Roman numerals of each of these numbers. So somebody's asking here, what's the difference between table and range? Okay, so range, you can do the things I'm doing with table with range, but it's a little trickier. Range, you're just telling it, make me the list of the first 20 numbers. You're not saying, you're not able to tell it, I want a table of this type of thing. In other words, the thing you're giving here is always just I just want the individual numbers, 1 through 20, for example. I could take those individual numbers and I could add 6 to them, for example. I can do operations like that. But if I want to put in a more complicated thing and say, make a table of a more complicated thing, this is an easier way to do it. All right, so let's go see how the Roman numerals did here. So we've got this table of lengths of Roman numerals. And now we can wrap yet another function around here. We can say list plot. Oops, if I could type properly, wrap it around there. And oops, okay, actually I made a mistake. It would have been better to say list line plot. And this is now going to show me, hopefully, this is going to show me for these Roman numerals, it's going to show me for each Roman numeral, how long was that Roman numeral. So we're seeing here that, for example, the Roman numeral for 100 is quite short, and Roman numerals for, I don't know which well, we could find out, like, if we wanted to have the computer do a bit more work, we could find out which number has the longest Roman numeral representation here. Okay, and I could show you how to do that. But are people following so far, more or less? I mean, the thing to understand, what you just wrote here, this is a real program. Let's see, we've got age range here. Okay, not so many actual kids here. Well, okay, I'm going to assume that I'm going to keep going, assuming that we're dealing with the young, and assuming, okay. So this is just, there's just some indication of so this is our program here, and we could do, let's do all kinds of things. Let's do this up to 1,000. Let's be more ambitious here. Okay, so this is showing us for all, let's make the computer do a bit of work here. This is showing us for all the numbers up to 1,000, what was the length of the Roman numeral representation of those numbers. Now, if we wanted to do some, data science on this, okay, let's we can copy that input. Oh, what could we do here? Okay, slightly more. Well, here, one question we could ask is, what's the longest for numbers up to 1,000? What's the longest representation in Roman numerals that's needed? So you just replace list line plot by max. So you're taking this whole list of lengths, and you just say, what's the maximum? The answer is 12. So we might want to say, let me think how best to do this. Well, we could say, I'm trying to think how to do this in the most obvious way. Well, okay, there's one easy way to do this. If we want to say, where does 12 occur in that sequence? Instead of saying max, we'd say position there, and then we'd have to say here, comma 12. And that's going to ask it, in this table of lengths, where does 12 occur? And so, oops, what did I do wrong? Help, help, help. What did I do wrong? That is terrible. What did I do wrong here? I'm very surprised that this isn't showing me, oh, very silly. Okay, I'm surprised it didn't color itself. Okay, my apologies. The good message there is actually read what the computer is complaining about, because it did actually say what the problem was. But this is telling us the number 888 is the number between 1 and 1,000 that has the longest representation as a Roman numeral. Okay, so well, we can do all kinds of things with this. Let's try something a little bit different. Let's try doing some things with words. So one thing that's a convenient function is random word. If you say random word of 10, you will get 10 random words, and everybody will get different ones. And it's kind of a fun thing to do, to see how many of these words you recognize, because you can use that to estimate what fraction of all words in English, let's say, you you know. But we could do, let's see, what could we do here? Well, let's do another kind of data kind of thing with words. So one question would be, what's the most common first letter for a word in English? Okay, let's see whether we can figure that out. So let me show you something. So if we get random words again, and then we say string take. So each word is represented by a string of letters, and string take says, take some number of letters from the word. So here what I'm going to do is I'm going to say, take just the first letter from each of 10 random words. Okay. And so if I do that, I'm getting a bunch of different letters here. If I wanted to, I could take, well, let me do this. Let me say, make a, we're always wrapping whatever function we want to run around whatever we wanted to give it as input. So we're giving this word cloud, we're telling it, make a word cloud of all of the letters that you went in there. Okay. So in this case, I got, so a word cloud just makes the letters that are more common in the list, it makes bigger, okay? So I just did that for 10 words, but let's say I do it for, let me do it for 100 words, for example, here. So this is now picking 100 random words in English. This is showing what's the most common, what are the most common first letters for words in English. So if people are following this, we could be more ambitious. Let me try this. I hope this is going to work. And instead of random word of 100, I could say word list, and then just open bracket, close bracket. And that will give us a list of about 40 or 50,000 words, which is pretty much all the common words in English. We could then run the same thing, hopefully. See, there we go. And so that gives us, for all the common words in English, that's telling us what is, what are the relative frequencies of first letters. So this is saying, if you have a dictionary, I don't know if people have paper dictionaries anymore, but if you did have a paper dictionary and you look at kind of how thick is the collection of S words in the dictionary, this is saying the S words will be the thickest section of the dictionary, followed by the C words and so on. Okay, so people getting that? So this is and we could try. Okay, if we want to really be ambitious here, we could try another language. Anybody? Okay, how many words is it considering? Let's answer that question. Let's just say length of word list. That's going to tell us how many words there are. So it's 39,176 words. Okay. For example, we could say, all right, let me show you how to do this. We could say take largest. If you want to know what's the longest word that's in its list, you could say take largest word list, and then you could say, sorry, take largest by here, string length, and then let's say 10. So, okay, we're going to try, okay, so this is showing of its supposedly common words, and it's very hard to know where you break this off, but this is showing, it's saying take largest by string length in the word list, take the 10 take the 10 words that have the largest value of string length in this word list. Okay, so it has some rather obscure words as its longest ones. We actually have word lists that are more complete than this, where the words will be even more obscure. Okay, somebody was asking about Japanese. We can go back up here, and we could say in here language. This is going to be, so type language, and then you type an arrow, and you type that by typing a dash, and then a greater than sign, a dash, and then that's a shift of a period on an English keyboard. And I'm sorry, it's a little bit trickier to type this, but let's see what happens if let me just try it, because I'm not absolutely certain it's even going to work before you waste. No, it does not support Japanese because Japanese is not an alphabetic. Let's try Russian, for example. So, okay, so there it did have a Russian dictionary. And so it's able to work out the most common first letter of a word in Russian. I think the problem is that for Japanese, I'm guessing that because it isn't an alphabetically oriented language, it's going to have more difficulty with that. I'm sure we can do some things in Japanese. So, for example, if I say something like, here's something I can do. If I say integer name, so let's say I have the number 456. Here's another function. Integer name gives you essentially the string, the way you say 456 as a string. So it says 456. So I'm pretty sure that, and this is where I have to go, if you hover over the name of the function and you press this little I sign, you will go to information about that function. And here, let me make this a little wider. This should be, okay, specify a language. Okay, all right, so then I should be able to say in here, Japanese, and because it's kind of a word, I have to put these quotes around it. So let's see whether I can do that. Let's see if this works. Let's see. Yeah, there we go. Is that right? I don't know. Okay. Somebody can tell me whether we got this right. I hope we got this right. Better have got this right. We could try, okay, somebody was asking for the longest words in Russian. All right, let's just try that. We could try, we're going to take language as Russian, and we're going to put that down here in our take largest by. And okay, Lesevoshternadov. I'm sorry, I'm really bad at this. Okay, now somebody was asking, can we pronounce it? How we'll do Klingon. Let's see whether we have any information about Klingon. I don't know if we have Klingon. I'll tell you what. We have a thing called word translation, and if I take a word like fish, for example, I can say, let's translate fish into Russian. And if we're lucky, it will give us fish in Russian. Rebar, yeah? I don't know. No idea. Let us see. I think it's very unlikely that we're going to have Klingon, but let's just see whether we do. I think missing, not available. Sorry, no Klingon. We can do, how about we do, all right, let's jump ahead to something. We'll do some more stuff with word translations, but I'm now led to, what was them that Klingons lived in? I remember Spock, at least, came from Tau Ceti. Okay, so let's, just for fun, let me show you something else you can do. An equal sign. You will get that little box with an equal sign. So hold down Control, press equals, and then type in that box. You can type Tor Ceti, Tor space Ceti, just like you type it in English, into that box, then hit Enter, and hopefully it will say it knows that Tor Ceti is a star. Okay, so now let's see. I have to go figure out what it can do here. Let's see whether we can do, let me go look something up here because I'm sorry, I don't remember. Let's see, I want to go search there. How do I get, that's very silly. I wonder how I get, well, I'm going to go over here. I'm going to cheat because I need to look up something. Oh, I'll tell you, Okay, let's. Okay, we're going to do several things here. Actually, first of all, first thing, let's see whether it knows the word Klingon. Okay, so we're going to type control equals and then Klingon. Okay, it does actually know something about Klingon. It says, oh wow, that's weird. It knows two things that are called Klingon. One is a language and one is a gene. Okay, so let's do Klingon as a language. And then let's say, we can say, all right, I'm just going to use something slightly more advanced here. I'm going to say quotes data set. And it should be telling us here what it knows about Klingon as a language. Okay, so it tells us that it tells us the original location of Klingon as a language was the United States. It tells us that it is a constructed language. It tells us that the language code for Klingon is TLH. So you may know, from websites and things, .en is the code for English. Apparently, Klingon has been assigned a code. It's .tlh, and here, let's see what it's what it can tell us about there we go. Okay. Wow. All right. It says that Klingon is written in the Latin script. That's just like English. It has a rather funny total number of speakers, 25 people. I don't quite know how it knows that, or whether that's even plausible. But it's guessing, oh, this is a little bit hard to read because this is showing other constructed languages. But so here, so we do know a little bit about Klingon. And we can, let's see, if we're into those kinds of things, well, here, let me show you some other things here. I have a great urge to switch to using, so what I'm doing here, I'm doing everything in the cloud. If I'm going to show you a bunch of things without so much following along, I probably can do it a little bit faster if I'm using the desktop. But let's use the cloud for now. Okay, so I was going to look up tau Ceti. I was going to say, what properties do we know of tau Ceti? And so one of those properties is distance from Earth. So we can ask distance from Earth. Okay, so that's that's telling us that tau Ceti is 11.89 light years from Earth as a star. I wonder whether there are exoplanets of tau Ceti. Let's see whether I should have looked at that here. Let's just look at its properties again. And let's see whether we know from here about its exoplanets. Let's see, I think I need to look something up here because otherwise I'm going to get this wrong. Let's see, exoplanets. Okay, I need to find out how I get, that's kind of weird, but let's see. I'm trying to work out how I figure out whether there are planets for the, and I'm sure there's a way to do that. Well, let's just try doing it by just saying tau Ceti exoplanets, see whether we can decode what that's about. Oh, look at that. That's a good sign. That's saying, what are the known satellites? So essentially what I was doing there was translating English into our language. Okay, there we go. Okay, so it knows about 4 exoplanets orbiting the star tau Ceti. And we could probably go ask it some questions about those. But let's go back. I'm getting let's well, let's see. Gosh, we could do some fun things. We could, if you're into science type stuff, we could try and see whether some of the laws that apply to our solar system also apply to the planets orbiting tau Ceti. Maybe we come back to that if people are interested. let's see. So somebody was asking here, I'm going to, if you take these brackets on the right and you double click the outer bracket, it will close up that group of cells. So you can do that as a convenient way to organize this notebook. And if you want to, you can also do things like you can sort of annotate what's going on. If you type Command 4, you click between the cells, press Command 4, and then you can put a section heading there, like you can say stars, for example, here. All right, but let's go back up. We're dealing with words. I was going to show you some things about word translation. So we didn't know Klingon here, but for example, one thing we might do, let's again live a little dangerously. Let's say word translation for the word fish into all the languages that we know about, okay? And or at least all the languages for which we have a translation. Okay, so this is now going to show us there's 170, well, at least 170 languages. So these are the most common ones: Mandarin, Chinese, Hindi, Spanish, Russian, Indonesian, and so on. These are the rarest, things like Latin and classical Quechua. So we can ask questions like, for the word for fish in different languages, what's the most common first letter for fish in different languages? So we can use exactly the same thing that we have to do one little tricky thing, because in these different languages, you'll see that, for example, I'm afraid I'm pathetic in terms of knowing human languages. I know a bunch of languages for computers, but not so many languages for humans. I do know Latin. I thought it was I see it's piscis, and the plural is pisces. So you'll see that in some languages here, it's giving several words as the translation for the English word fish. And that might be, we didn't tell it fish in what sense. It could be fish as a noun, fish as a verb, and so on. So let's go here and let's just say, so for each of these, in order not to confuse it too much, let's just pick the first, let me see if this is going to work. Is this right? Is this what I want? No, not what I want. Sorry. Okay, delete that. I got it wrong. Okay, unfortunately, we have to do something a little bit trickier here, which I can explain to people. We want it to use, okay, I'm going to explain a little bit more kind of computational language stuff here. That symbol is going to tell it, apply, do this first thing separately on every different language, okay? Let me try and show you how that works. Okay, so I've already been showing you that the way everything works is like with functions. Like you'll have a function like, I don't know, something like range we showed before, range of 10, that does something, okay? But if we wanted to be a bit more abstract, we could just say f of x. And that will be if f had been range and x had been 10, then it would have actually done something here. But if we want to, we can just have this function f that didn't do anything. It just said f of x. F could be range, f could be Roman numeral, f could be all kinds of things, but it's just f here, okay? So another way we can write that, we can write it as f at sign x. And that actually just is a different way of writing f of x. The computer will interpret it exactly the same way. All right, so let's say we say f, and we say ABC here. It will just say, okay, you want this function f, and you want to make it do something on this whole list of things ABC. Doesn't know what to do because it doesn't know what f is, but that's what you're asking it to do. I could equally well say f at sign ABC, and again, it'll just interpret that as I want f to be a function that is operating on this whole list ABC. But another thing I might want is to say for each one of A, B, and C, do f on it. And so I can represent that by saying f / at ABC. okay? And that's what we were doing here. We said we wanted to get the first word in each language. So we said first /at, and then this whole thing. And that told it, don't just ask for the first thing in this whole list of different things, but for each thing, get the first word in that language, okay? So now we can do the exact same thing we did before. Remember, we did that string take thing. Oops, did I just delete that? Silly me. Okay, what did I do? There. Okay, click there, press type string take, comma 1. And so what I'm now going to do is I'm telling it, take the first letter of the first word that is being used for the translation for fish in all these different languages, okay? So it's going to have to think for a little while. Oh, what did I do wrong here? Oh, silly me. Oh, dear. I need to do something. Oh, dear. Sorry, it's going to be a little bit more complicated. Oh, dear. Humph. All right, I'm going to type in something that's a little more complicated here. Oops. Yeah, this is where telling the computer exactly what you want got a little bit more complicated. This is, so because what I need to do is I need to tell it, okay, for people who know fancy computer stuff, this is a pure function, an anonymous function, a lambda expression. That's a very fancy thing. Let me just run this to show you what it does. What that's doing is it's saying for each of these things, work out what the first letter is for that word. And so now here, I could take that whole thing and I could say, make a word cloud out of that. And hopefully it will be able to figure out. It's recomputing that. Oh gosh, I need to do one more thing. Sorry, this is what I get for I need to tell it. Yeah, okay. This hopefully will work. So this is going to, there we go. Finally, we got it to work. Okay. So this is showing us for all languages that it knows. Let's see if we can read this code. Okay. So it says, find the word translation for fish into all languages. Now, and this is a bit tricky. This is saying for each of those languages, take the first word for fish in that language, take the first letter from the string that you get from that word. This is telling it, I don't want to know about what languages these are in. I just want to know what the words were, and now make a word cloud out of that. So this is saying that the most common first letter for fish, just like it is in Latin, for example, or in French, but not in English, is P instead of F. Obviously, there are languages here that don't use the Roman alphabet, and so those are showing up in a different way. If I really wanted to, let's see, I could do something here where I say, let me see what I want to do here. I could say transliterate, and that will try and convert all of those non-English scripts into an approximation, if it can be done, into an approximation. Oh, that's interesting. So when we did that translation, no longer is P out ahead. The M sound seems to be the most common first sound for the word for fish in all these languages. Rather than P. It's kind of interesting, actually. All right. Let's see, a question here. How does using a random framework for making a graph of letters get a random word teach anything about computing? Okay. Well, what is computing? Computing is about getting computations done. And I think the question is, so sometimes people think, what can I say? What's going on inside to compute things here is we're using both being able to compute and being able to know things about the world. All right, we want to do something that's more crunchy and more computational. What could we do? We could do, let us do something, let's do something that might be, let's do something that involves images. That might show something that has, or let's do some machine learning. That's always a good thing that is really definitely computational. So let's say machine learning here. Okay. So let me try and give. So what is machine learning about? It's typically about being able to, instead of us having to write a program explicitly, it's about having a computer be able to learn from examples of things. But let's get some idea of how that might work. Let's try. Where should we start here? Let's do this. Let's take the alphabet. Okay, so this will just be an ordinary English alphabet, and let's make. I'm going to use that /@ thing again because I want to say make an image out of each of those letters. Okay, so each of those letters is now going to be, if I can make it bigger. Okay, so that's now just a collection of pixels. Okay, so it's just showing how the computer would display on the screen that letter. Actually, I'm thinking maybe I'll show something else first here. No, I'll go ahead and show this. I'm being challenged to show something that is more obviously a computer computing something. So let's see what we can do here. Let's see what we can do. All right. Let me think of how I'm going to do this. So okay, so that's going to make little pictures of all the letters of the alphabet. So let me show you another thing you can do. You can say feature space plot of this. All right, and now it might take a little while to do this. Let's see how long it takes. Okay, there we go. Okay, so what did this do? So the question is, if you are looking at those letters and you are asking the question, which letters look more like, oh, what just happened there? That was really weird. Let's run that again. What on earth did that just do? It's really strange. It's making me nervous. What is it doing? Help. That is a very strange thing for it to have done. Well, I'm going to switch to doing this just on my computer. But I don't know why it did that. It's okay, let me do this just on my computer here. Okay, so here I've got so here what I've done is I'm saying take the pictures of letters of the alphabet and just a second. Okay, so we're taking these pictures of letters of the alphabet and we're asking the computer to do something for us. We're asking it to tell us which letter looks like which other letter. Okay, so we might say, well, you might say, I don't know, you can decide for yourself which letters you think look like which other letters. You know, like Q looks a bit like D and things like this. Okay, why do we care? Well, we care because if we wanted the computer to recognize these letters from just a picture of the letters, It's this is what we need to get started to figure that out. So let me show you something, and I'm kind of people are asking various questions, which I'll try to answer here. But let me give you an indication of why we might be interested in this. So let's try taking. Let me get a anybody got a favorite animal? Let's say picture of a fox. So I'm now just using English language, and that's saying that's a red fox, an image of that. Okay, it's going to give me an image there. And now I've got a function that's called image identify. And we could say, take that picture of a fox and try and identify what is that a picture of. And let's see what it says. Okay, very, very impressive. It said, I mean, of course, in this particular case, it was a picture it had generated, so it's a little less impressive that it could recognize that that was a fox. If we let's do this. If we really wanted to, let's say we do a web image search for a fox. Who knows what we're actually going to get here? We might get some very goofy things. This might not work for everybody in the cloud. It will work if you have a desktop version. Okay, so we've got some pictures of foxes that we just got from the web here. And now let me say image identify here. And I'm going to use that, I want to identify each picture here. So I'm going to use that /@ and I'm going to use the thing %, which just means the most recent result I got. So now it's going to say, what is each of those things? Okay, so it says most of these were red foxes. One of them is something I've never heard of. I don't know what that is. We can try and find out what that is. Okay, let's can take that and we could say word definition. Let's see what it says for this. Oh, okay, a Siberian breed of white or cream-colored dog. Okay, I did notice as I was scrolling through here that distinctly looks white. So that's a good sign. But anyway, so this is an example of sort of AI machine learning being able to identify what are these pictures of. And so what I was kind of trying to show you was a little bit of an idea of how that works, how it manages to figure out what is that a picture of. And so I was going back up here and showing these letters of the alphabet. And if we put in some new letter, what we're really going to be asking is, which thing in this arrangement here, which letter is the thing that we are now providing closest to? So let me give you an example here. This is going to, I'm going to accelerate a little bit, so this is going to be a little harder to follow along with. But let me show you. Let me show you something. I'm going to show you how we might teach the computer something. And this is what I'm going to show you is a very standard machine learning thing, which is we've got examples of handwritten letters, and we've got and it says that thing there is a handwritten version of a 0. Okay, and so what one thing we can do is let's take from here, let's take a sample of, let's say, 500 of these examples of that's an 8, it's an 8. That's a 0, it's a 0. Okay, and we could tell it, given those examples, as a human, if you're learning, how to write numbers, you might say, okay, that's what a 4 looks like, and then you could potentially learn, if I was trying to learn, I don't know, the Russian alphabet that I know only a little bit, I might look at a bunch of examples and try and learn from that to recognize each letter. So we can actually tell the computer, we can say, learn from the set of examples, and we can just say, classify means learn to classify these pieces of writing according to okay, so this is showing basically the computer doing it's sort of giving an indication of how the computer is learning this, and it's going to hopefully give a result here. Okay, there we go. Okay, so what it did was it gave a result where it learnt from that data how to recognize things. So if I take that, oh, whoops, I'm going to need to say, let's just say, let's call this, I'm going to do this again, and this time I'm going to say, I'm going to make a thing which I'm going to call CF for, let's say, classify function. And then what I'm going to do here is, so this is making kind of my own function for recognizing digits, and I could go and I could then say, use my classify function to try and recognize that digit. And it says, oh, that's a 0. Great. So we could get some idea of how it recognizes different kinds of things by taking, let's do this. Let's take a, I'm going to just say, take 50 numbers, 50 handwritten digits, and show me this thing that says which handwritten digit is like which other one. So what you're seeing is that the computer figured out that all these things that look to us like zeros are similar looking. All these things that kind of look like 7s are similar looking. These things that look like 1s are kind of similar looking. There's this cloud of 6s down here. And so when we're telling it to learn how to recognize a 0, what it's effectively doing is making its internal version of something like this and saying, I'm going to make a collection of make this be the things that I'm calling zeros and so on. So let's see. I mean, we can. I'm not quite sure what direction to go in. Somebody is saying that we're not talking enough about computation, but I think these things are. Well, let me. I'm just trying to give you sort of a sketch. Let me try and give you sort of a sketch of what. Let's talk a little bit more big picture about the idea of computation. Okay, so one of the sort of most important ideas of computation is that you can represent sort of anything you want to talk about as data that a computer can deal with. So, for example, we might have a number, we might have a word, we might have a picture, one of these images. All of these things are being represented in a way that a computer can understand. And so we could ask, what ultimately, the reason that we're able to do all these different kinds of things is that in the end, all of these things are just represented in the same underlying way that a computer can understand. So let's take an example of how things are represented. Let's take colors, for example. So let's say the color red. Okay, so how does a computer understand something like the color red? So what it has to do is it has to effectively convert it to something that that's sort of the same kind of thing as a number, let's say. And so for colors, there's a way known to sort of convert colors to something like numbers. And that way is to say any color that we humans can perceive can be corresponds to a certain amount of red, a certain amount of green, a certain amount of blue. So for example, we can say red, green, blue color. And for example, we could say, I don't know, 1, 1, 0. And that means I want a color that has lots of red, lots of green, and no blue in it. And that's yellow. And then we could say, for example, remember we used table before to make tables of things. here, for example, we could say make a table of numbers where we have the color here with X going, let's say, from 0 to 1 in steps of 0.1. So that's going to make a sequence of colors. So it's using the fact that every color can be represented just using these three numbers. And it's now making a table of colors where each color is corresponds to well, color with value 1, with value X that goes from 0 to 1 in steps of 0.1, and then 0 blue. So for example, we could go and generalize this. We could put a Y here. We could say here Y 0 to 1 in steps of 0.1. Now we'll get an array of colors, but underneath, these colors are all being represented in terms of, in this case, sets of three numbers. But that's showing us the possible colors that are represented this way. And all these different kinds of things that we're looking at, in the end, are represented in terms of, in terms of kind of a version of numbers. We can, for example, for colors here, let's see if we can figure out how to do this. Let me think for a second. Let's see if I wanted to show you all three colors varying. So I could say X, Y, and Z, and I could vary them all from 0 to 1. Then we should get kind of all the different kinds of colors that we can represent. Oh, it's a big long list because it's how is it going to show us the colors in how is it going to show us these three dimensions of colors? Well, let me think about that. I think I know a way to do this, but it's going to be a little bit trickier here. Let me try doing this. So I'm going to try to show you something where I'm just making all the possible colors. Let's do this. Let's say we make just to give you an idea how this would work. Okay, I'm going to make little cubes that are each in a particular color. Let's see if this works. Oh yeah, it did work. But now what I want to do is make that be a little bit smaller. Let's see whether that works. No, it's not what I wanted. What's the best way to do that? Well, actually, here's a way to do that. Okay, oops, let's make that down to point. Oh, I see what went wrong. Let's do this. Okay, so what that's going to do, what that says, let's read the code that I wrote here. So that says make a table of spheres. And now, I'm sorry, this is a little bit more advanced. I can explain it if people are interested. That's a sphere at coordinate position X, Y, Z in 3 dimensions. The sphere has radius 0.1. The sphere is styled to have a color X, Y, Z. And then we're saying make a table of spheres, and there we get the result. Okay, so what that's showing is it's kind of giving us an indication of how color can be represented. We've got in one corner of this color cube, we've got blue. In another corner, we've got green. In another corner, we've got yellow. We've got white, which corresponds to all 3 red, green, blue colors. That's and we could do let's see, what could we do here? We could do all kinds of things, just lots of fun stuff. But somebody was asking, okay, a couple of questions here. Is there a step? Let's see. Well, if we wanted to, let's say we want to get every second number, we could say with many different ways to do that. Let's say we say 10 numbers. We could say 2 times that. It will give us twice each of those numbers. Another thing we could do, we could say make a table of, actually we don't need the star, we can just say 2n, n goes up to 10. That'll make those numbers. Now, if we want to make a plot that has that in steps, well, I happen to know that we could use list step plot to do that. So let's just put that in there. Okay. So somebody was asking to plot every second number. I'm not sure that's quite what you were asking, but that plots steps for each number going up by 2 at each step there. I could do that at a lower level if I wanted to as well, but this is just a convenient way to do it. Okay, so another question someone was asking was, what's the minimum set of functions needed to get started with Wolfram language? And I tried to figure that out for my book about Wolfram language, and I really oh, actually, I forgot to do something here. I could have done this. Would have been good, actually. I kind of tried to do that, and each section here, I kind of give a little vocabulary at the end, showing sort of the functions that got used so far. So here is just the different ways to do this, but here's something where I'm just using essentially 5 functions, and then I'm able to do all kinds of things just with those 5 functions. But what I found is, once people get the idea that you can have a function, you can have a function of a function, and so on, that then it's really just a question of telling them, oh, there's a function that does this, and then they're off and running. It's not very difficult. Once you have the sort of structural idea of writing down functions, it's not so difficult to go and build something up in some different direction. So, for example, here, you look down here, I mean, some things that sound is always something that that works well if you're just starting out learning things. It's not so great to do sort of through the cloud, through this kind of remote mechanism. Another thing that's often interesting is geo-computation, doing things with different places. So, for example, we might that's always that's always something that's quite interesting and kind of exposes both using sort of data about the world and computing things. Anyway, that's a little bit of an indication. Now, I'm happy to kind of take requests for different kinds of things we can compute about. It's a little difficult because usually I've done this kind of thing. Well, I haven't done this so much with adults, I have to say. I leave that to other people to try and explain computational things to adults. But I've done a fair amount of this with kids because I find it interesting, and I found that it's one of the constraints is that once you can see kind of what people are understanding and how easily they're understanding different kinds of things, it's easier to know kind of how fast to go and in what direction. But let's gosh, I could go in so many different directions, but if people have a request, okay, somebody's asking, how do you text your friends? All right. Well, you can do a little bit of that. Let's see what we can do. We could do, I am not sure, we can certainly do send mail. If you say send mail hello, you should get, oh, it's asking me to, okay, hold on. It is asking me to authenticate myself. Okay, great. So I think you'll be able to do that in the cloud, and you will at least be able to send mail to yourself. I don't think the cloud will let you go and start spamming everybody, but you can at least have fun sending mail to yourself, and you could take a picture you've made and you can send, I could take this picture here and I could say, send mail that picture, and it should just go ahead and send that mail to me as a picture. We can, let's see, in terms of, there is actually a way on, if you're using the desktop version, there's a function called send message, which will actually send text messages. but let me not. I don't think that's supported in the cloud version. But you can. Okay, so something you might do. Oh, I don't know. Let's take an example of a thing to send your friends. That's a good example of that. How about we do this? If we say random entity, given name, okay? And that's going to give us, let's take 10 random names of your possible friends. Okay. Wow, those are really weird names. Those are, well, not weird, they're just interesting, actually. That was in our whole database of all given names. We just picked 10 names at random. I didn't pick the 10 most common names. I can let's do that. Let's see. Well, let's take for any one of these names we can find. Let's just see what properties this name has. We could find things like okay. Well, we could find, let's find age distribution. So, oh, that's odd. Oh, maybe I did. Okay, sorry. Let me do that again. Let me do that again. I do not know anybody with that name. So, let's see. Oh, I see. I need to do that. All right. This is showing me if I say, let me do this. Not what I wanted. Let me do this. Hold on. Sorry, I have to. Okay. This is showing me for that name. Sorry, I have to do some slightly more advanced things. That's showing me for the name Escher. It's showing me what the most likely, most likely, okay, so there's a Gretchen age 10 here. So let me just, since there's a Gretchen age 10, I'm going to type in the name Gretchen here, and I'm going to ask what the distribution of ages of people named Gretchen is. Okay, so this says if you go out there, so you're down here, and you are actually a comparatively rare 10-year-old named Gretchen. The most common age for somebody with the name Gretchen seems to be around 38 or so. We can try. Let's try for some other names. Let's try for my name. I bet there's a bunch of old fogies with my name. Yeah, look at that. That's terrible. My name is common. You know, my parents always used to say that they'd been very innovative in coming up with my name. This proves that that was simply not true. That it was a very common name at about the time I was born. But this is showing you showing you how that works. Oh, people are asking, will I cloud publish this notebook? Yeah, absolutely, I can do that. Actually, I can show you how that all works. Well, okay, a couple of different requests here. Can show you how to publish all this stuff to the cloud. Let me just go ahead and do that. Hold on 1 second here. I am going to live streams. Okay. Well, this from the desktop, I can I could publish this desktop notebook, or I can publish my cloud notebook. Let me publish my cloud notebook here first. I'm just going to name it. I'm actually going to just say publish, and I'm going to specify a name. I'm going to say Intro for Kids 01, and I'm going to press publish, and now it just got published. And so here, that QR code, if you go to that QR code, and I'm very much I feel like I have to do this with my phone just to check that it actually works here. So let's just do this. Let's see what happens if I go to that QR code with my phone and press the button. And I should, if all works according to plan, yes, indeed. So I will get the published version of that notebook will now be available from that QR code. And we can send out, somebody can send here in chat the URL for this. Let me just copy this and what do I do here? I just say copy that, send it in here, okay. And I can similarly, if I'm going from the desktop, I can do the exact same thing. I can just say publish to cloud, and I will publish that as intro. What did I call it? Intro for Kids 02, and that will now get published, and that will also be available. Let me just copy that there to the clipboard. Okay, so there's a question wanting to know, yes, the homework is find the top 10 names that last the longest. That's a good idea. That's interesting. That would be an interesting thing to do. You know, what is the name that has stayed as popular for the longest? We could do that. That's a good piece of data science. Okay, how do you make tables and charts? All right. So, well, let's see. First, we have to have some data we're going to make a table out of. I showed you a little bit before how to make, so let's make table makes tables of things like numbers or words or whatever else. So I could make a table of, let's say, n squared, n up to 5, for example. That will, that will make the sort of the raw data. Now, if I want to turn that into a visualization, one thing I showed before is list plot. List plot will just plot those numbers on a graph. So there's the 1, 2 goes to 4, and so on. That's one type of thing I could make. I could also say something like bar chart. So this will make a bar chart of that same data. Or I could say something like pie chart. That will make a pie chart. So that's showing, a pie chart is kind of a weird thing to make from this data, because there's the 1 value, the 4 value, the 9 value, the 16 value, the 25 value. So that's kind of that's how you could make make a chart. Let me show you a more elaborate chart that we could make. Let's do this. I'm going to show you, let's take something like the 10 largest cities in the world. So I can do that as using something a little bit fancy. But just let's bear with me here. Yeah, that should work, I think. Oh, oops, I have to say make a list of those things. Okay, so this is the 10 largest cities by population in the world. So that's also some data. And now I could say, let me somehow make a visualization of that data. So I can say geo list plot. So instead of list plot just takes numbers, but geo list plot takes geographic places. So that's showing me where the 10 largest cities in the world are. Or for example, I'm just curious actually myself, if we go to the 20 largest cities in the world, let's see where they are. Okay, it's interesting. Actually, I'm motivated. I want to see the let me look at the 50 largest cities in the world. Okay, interesting. Okay, what the US it centered the plot on the place where there was the most density in Asia here, in China, but I guess New York just made it on from the US here. Actually, we could just to show you kind of how to make sort of charts and tables and things, let us say I wanted to make a little bit more complicated. I could make a bubble chart that shows each of these cities with their population displayed. Actually, I'll tell you what. I've got a computational thing to do. Somebody was challenging me to actually compute something here. So let me actually compute something here. So I'm going to take. Actually, I'll tell you what. Let me take. I probably can just say 10 largest cities in English here. Could just say 10 largest cities, and there's a decent chance that I will get that out. Let me see. I probably have to say, show me the actual list of those. Yeah, there we go. Okay. So if I can just do that with English, I could say, let's say 30 largest cities. I could actually, let me put this first just because I didn't, well, okay. That's just like saying, okay, so there's my 30 largest cities in the world. So let's ask the question. So given two cities, I can find out how far is it from one city to another. So for example, let's say, I don't know the answer to this. I'm actually curious what that distance is from Shanghai to Beijing. How far is it on the Earth? Okay, so it's saying it's 663 miles, roughly, from the center of Shanghai to the center of Beijing. Okay, so now let's ask the question. Imagine that I want to do a grand tour, visiting each city here in turn. Okay, so the question is, if I want to do that, and I want to pick the shortest path between those cities, how should I go? So Lagos is in Nigeria. If I went, let's say that my path was, first I go to Shanghai, which is in China, then I go to Lagos in Nigeria, then I go back to Beijing. That's probably a pretty bad way to visit all these cities with the shortest path. Instead, I'm going to want to go to the cities in China first, then I'm going to jump over to Africa, then I might jump to South America and so on. But it's actually a kind of hard problem to figure out what's the shortest path between all these cities. But we can ask the computer to do that. And let me, let's call this cities. And now let's ask the computer to figure out the shortest path between these cities. It's a thing that if you do computer science classes, they'll call it the traveling salesman problem, because the sort of classic version of this problem is you're a salesperson who's going to visit different cities selling some particular product. In the days before you could do that with video conferencing, and you were actually driving around from place to place, and it's what's the best order in which to visit them in to cover the most cities by going the least distance. But here, let's see whether we can do this. I'm not sure if we can just directly say this, but let's try it. I'm not sure if we can do this. Let's just see whether the computer complains at us. Oh, no, it managed to do it. Okay, so what this said was, find the shortest tour through all those cities. So what it's telling us is there's a 35,000-mile tour that visits city number 1 first, then 9, and so on. Okay, so what I'm going to do here is I'm going to say, take those cities, and I want to show them in the order that corresponds to the order that it gave here. Okay, so it's saying I go to Shanghai, then Tokyo, then Seoul. Okay, it's interesting. I don't go straight from Shanghai to Beijing. That's kind of interesting. Okay, so let's say geo list plot of that, and then I want to join them all up. And let's see. Okay, so that's now showing me if I want to visit the, how many was it? I forget, 25 largest cities in the world. What's the shortest path that I can go to visit all those cities? Someone was asking, is that, how does it figure this out? It's actually a pretty fancy algorithm. It's kind of I think we have the best algorithm anybody has for doing these kinds of what are called combinatorial optimization problems, traveling salesman combinatorial optimization problems. The most obvious thing you would do is just try every possible ordering of these cities. Okay, let's see how many orderings we'd have to try. So how many cities were in this list? It was length of cities. Okay, so for people here who know fancy math, if we want to know, let's say we have 3 things, 1, 2, 3, and we want to know how many ways are there, how many orders are there for 1, 2, 3, 4, for example. This will show us all the different orderings. So if this was possible tours, we could visit city 1, then city 2, then city 3, then city 4, or we could city 4, 2, 4, 2, 3, 1, and so on. So the question is, how many orderings are there? So for 4 things, the number of orderings we can work out here is just the length of these permutations, and it's 24. If we have 30 cities, I'm using a math fact, the number of orderings is 30 factorial, and that number is that. So that's a pretty big number. And if the computer had to work out for all those possible orderings, it had to work out which one was shortest by just working out all those orderings. It would take a really long time. Let's just see how long that would be. So how fast does my computer run? Let's see, it probably runs at, let's say, gigahertz. That means it runs 1 billion instructions per second. So let's say it just took 1 instruction, which is really optimistic, to work out each of those possibilities. So we would have to say the number of seconds that it would take is 30 factorial divided by 1 billion. 1 billion is, I can just type in 1 billion. Here we go. And I'm just going to say, just give me a number for that. So that's, okay, sorry, that went to scientific notation. That's the number of, let me just write that out. Okay, that's the number of seconds, roughly. It doesn't know the exact number of seconds based on what it has told it here, but that's the number of seconds it would take if the computer was doing 1 billion of these things per second. That's the number of seconds it would take to work out the work this out. So just to give a sense of scale, let's just work out if it took that number of seconds. Let's say it's this. Let's say seconds, and so it's that number of seconds. And let's see how many years that is. Let's convert that to years. We're asking it to convert to years. That's still a huge number of years. Let's divide that by the age of the universe. So, okay, so this says if we were doing it if we were doing that 1 billion times a second, if we were working out different ones of these what are called permutations, a different possible ordering of cities, and we were doing 1 billion of those choices per second, it would take us 600,000 times the age of the universe to work out the answer. So that's clearly not how it's doing it, because it managed to do it in a fraction of a second. And the reason it's not taking that long is because it has a clever algorithm that allows it to work out the answer much more quickly than by just trying all the different possibilities. And I could probably show you an example. Yeah, let me show you one example of how one might actually do an algorithm for something. Okay, so let's do sorting. So let's imagine that we wanted to, let's see. I'm going to do something kind of super advanced here, but I'm going to use something super advanced, but I'm going to use it in the service of something that's not so advanced. Maybe. What's the best way to do this? I'm going to try and show you. Well, this may not be as easy as I think. What I was going to try to show you is if you were trying to sort this list of numbers into order. Okay, so really 1 should be first, followed by 2, followed by 4, followed by 5. Okay, so we know how to do that. Just sort it. Okay. Let me see. What's a good way to do this? The question is, what how would you do this if you were trying to work out how to sort these numbers? And so a thing you might do is to say, let's look at, for example, every pair of numbers, and let's say, is that an order? No, it's not an order. Let's put it in order. Okay, let's look at the next pair of numbers. Is that an order? No, if it is an order. So what we could do, and I'm just thinking how I can best do this for you. It's a little bit complicated to write a really short piece of code that does this, although it is very beautiful actually if we did that. Let me just see. Let me just look at something here. I think we might have an example here. Maybe not. All right, I'm not going to be able to do this probably. Okay, let's try something here. So let's to give you an idea about how algorithms work. Okay, let's do something even much simpler than that. Okay, let's work out. We take two numbers, okay, and we multiply them together. Okay, so if you know long multiplication, which I barely do, you know that you put these numbers, you write out these numbers, and each digit in each number, you basically multiply by each digit in the other number. Okay, so for every digit here, if there are, let's say, 10 digits in this number, for every digit here, you're doing 10 multiplications in the other number, with the other number. So that's 10 times 10 different operations. So if you said there were n digits, where n can be anything, 5, 10, 50, 100, whatever, if there were, let's say, 50 digits here, it would be 50 times 50 operations that you have to do that multiplication, okay? So what that's telling you is we can make a table. If there are n digits, it's roughly n squared operations to do multiplication the way that us humans get taught to do multiplication, okay? So now we can ask the question, well, how fast can the computer do multiplication? So let's give it some typical multiplications to do. Let's to work out multiplications, let's make a random number. Let's see. I'm going to make well, to do this without cheating, I'm going to do this. Sorry, a little bit more complicated. I'm going to make a number between, so this is going to make a number, let's do this. This is going to make 10 numbers, let's say with n is 20. Do this. This is going to make 20 random length. What did I do here? Did I get this right? Oh, yeah. I'm sorry. I got myself confused here. This is making 20 random length 10 numbers. So if you're thinking math like, this is numbers between 10 to the 19 and 10 to the 20th. Okay, so those are numbers with 20 digits in them. Okay, so now I've got these numbers, and now I'm going to ask the computer to multiply a pair of these numbers. So I can just take that one of those numbers, and I can say, well, actually, I'll tell you what. Let me first select. Let me select 20 numbers, and then let me make. I'm going to use another slightly advanced thing. I'm going to make all pairs of those numbers. Okay, and then what I'm going to do is I'm going to say for all those pairs of numbers, I'm going to again. Sorry, slightly advanced. I can explain what this is doing, but this is just an easy way to multiply all those numbers together. Okay, so this is going to be a way to tell the computer to multiply together multiply together in all possible ways these numbers of length 20. Okay, so what I want to do here is I want to say. Let me do this. Again, I'm slightly, for people who know programming, but let me just show you this for the sake of getting an answer here. let's say I want timing of times of that, and I want let's just check something here because I need to remember how this works. Okay. All right, so this very slightly complicated thing is going to time a bunch of computations done with a bunch of these multiplications, okay? So now what I'm going to do is I'm going to make a table, and this table is going to be for numbers from length 1 to, let's say, 30. I'm going to work out how long does it take to do those multiplications. Okay, so I'm going to ask it, I'm multiplying a bunch of numbers of length 1 through length 30. Actually, I'm going to go much further now. I'm going to go to 100. Oh my gosh, this is too fast. Let's go to 500. No, this is still too fast. Okay, what I was going to try to show you was how, as we increase the length of the numbers, remember I said that the way us humans do these things, it will, silly me. Sorry. The reason this was so fast is because I got it wrong, and we were always working it out with length. Okay, let me just do this. Sorry about that. That was very stupid on my part. Okay, hold on. Just let me get this right here. I want to say tuples of that. There we go. Yes, okay, wrong. That is this. Sorry. There we go. Okay, here we go. This is more like it. Okay, so now what this is doing is, sorry, this code is a little bit complicated, but what I'm doing is I'm telling it for numbers from length 1 to length 10, I want to know how many seconds did it take to do those multiplications. Okay, so let's do it for numbers up to length 100. So what this is saying is, remember what we predicted was that for a number of length n, the time it will take us to do the computation should be n times n. But I don't think it looks like it is n times n here. It looks like it's much faster than that. And am I still getting something wrong here? Don't think so. I think I'm getting this right. You know what? I'm just going to check one thing. Well, let's just try this. Okay, let's go 100 to 1,000, length of 10. Wow. Okay, let's go to 10,000. So these are now numbers. We're finally spending some effort here. All right, let's do this. This is going to work better. Okay, we're finally taking effort. Okay, so this is numbers of length 10,000 digits. Okay, we're asking how long does it take to compute this thing with numbers of 10,000 digits. All right, so let's make a plot of that. And there's the result. So this is showing as we are increasing, it's actually a remarkable plot. So remember, the way that us humans are taught to do multiplication, if we had a number with 100 digits, for example, we would have to do 100 times 100 operations to work out to work that out. So in this case, if we were given a number with 10,000 digits, we would have to do 100 million operations to work out what the answer was to that multiplication. But in fact, the computer uses a cleverer algorithm to do it. And we can see that the amount of time it takes, if this was, I'll show you what it would look like. If it was, if we said, well, if we just said table n squared, n goes up to 50, let's say, this would be, it will be going up like this. And we can see that at 50, it will be taking 2,500 operations to do this. Okay, so here, even at 10,000 digits, it's still doing it in all those operations in 0.004 seconds. So let's live really dangerously. I'm curious what will happen if I go to 100,000 digits, see how long it will take. This might take it a while. Let's just see. This is being kind of cruel to my computer because it's asking it, okay, that's quite interesting. So that's showing how the length of time to compute numbers with 100,000 digits. Up here, we're computing with numbers with 100,000 digits. So this is an example of one of the things that's been sort of discovered in inventing algorithms for computers, is how to do operations like multiplication much faster than us humans knew how to do it. And the methods that the computer uses, you might say, well, why can't I do my homework faster by using the methods the computer uses to do multiplication of numbers? You wouldn't want to do that, because you would have to do the setup for how you do that multiplication would take you an hour to set up your multiplication. But once it's up and running and going, it can be done very fast. And it's also a very non-human process. It's something where you just do a lot of operations to get started. If you're only doing like 3-digit numbers, this method that the computer uses is completely silly. It involves doing an hour of setup to do your three, for a human, it would take an hour of setup to do the multiplication. But if you're going to do an operation with 100,000 numbers, 100,000 digits, it's worth spending that time. It's worth the computer spending the time it needs to spend to set it up to do that long computation. How fast is my computer? I have a fairly fast computer here, but you know what? You can do the same thing if you do it on our servers here in the cloud. I bet all of you will be able to do this within a factor of 2 of the speed that I'm doing it. Let's see. So I can probably work out. It's kind of hard to know how fast my computer really is, because it's a question, doing what? Somebody's asking here, does the algorithm change its methods based on the number of digits? Yes, it does. So for people who know fancy stuff here, it initially it uses an algorithm which takes about n to the power 1.3 something, and then it goes to n log n, and then it goes to n log log n, and then n log 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 n. And actually, it's very close to just linear in the number of digits eventually. And it's switching between different methods as the number of digits gets larger. Oh, we're asking advanced questions. Yeah, you're doing, this is, okay, all right, I'll show you. All right, let me show off something about my personal computer setup, okay? Because I've been working on a big project that, okay, so let's say I do, I want to, so now what I'm going to do is I'm going to say, so normally when I'm working out something like 2 + 2 or something, it's just doing it on one computer. But if I wanted to, I could do a computation on lots of computers. And if I say parallel evaluate, that will do things on all the computers that I have set up to compute on. So for example, let's do this. Let's say, let's just ask it the names it's got, well, yeah, okay, I'll tell you what, no, let's just tell it to work out in parallel a bunch of random numbers. So random numbers up to 1,000. And what it's going to do, you'll see it do it. It's launching, this is me showing off because I've got a lot of computers that I'm running. This is showing off, it's starting up 37 different computer cores, 49 computer cores. That's a computer in my basement, up to 61. Okay, that's another computer. So we've got 93 different computations that I can run in parallel. So that's an example. So I don't know if I did, what's a good example of something I could run in parallel here? I could say, what can I run in parallel that you guys would easily appreciate? Well, the problem is that if I run something in parallel, it takes, well, here, I can just ask my computers what their names are, and it'll show me each computer, different computers. Okay, let's do this. This will tell me how many different copies of the program are running on different computers. So like I have a computer called Threadripper that has 32 CPUs in it, and so it's running at 32 times. We can, let's try running, let's see what computation I can run that will be on all these different computers. Let me, all right, I'll try one thing here. So some of you guys will have heard of prime numbers. Somebody's asking me to do MapReduce. Sure, I can do that. That's a little bit advanced. But let's see what I can do here. Okay. Well, let me try doing something here. Let me try. What can I show you that it's not too advanced? All right, I think I can do this. Let me show you something. All right, let's try. See how long that takes. It doesn't take very long. Oh boy, that doesn't take very long either. Oh, that doesn't take very long either. I'm having a hard time finding a computation that takes a long time. Too fast. Well, let me think here. See, the problem is what I'm too fast. Somebody's asking how many digits are pi? Okay, well, we can, I'll tell you what, I've got an idea. Yes, I've got an idea. This is a good idea. All right, let's try doing this. All right, so pi, ratio of the circumference of a circle to its diameter. People know its value is about 3.1415926, et cetera, et cetera, et cetera. Now, I think if I do this, I should be able to, let me remind myself how this works, to pick out yes. All right, let me try this. Base 10 digits, length, let's say 1,000,000. Oh, no, 10, starting with the 1,000,000th digit. Okay. That's not what I expected. Starting with a coefficient. Oh. B to the n. There we go. Okay. So these are the digits of pi. So I just worked out a bunch of digits of pi. But here what I'm asking it to do is to work out the 1,000,000th digit, the 10 digits of pi that are about in the 1,000,000th position. Okay. So, okay, that's a good idea from somebody on the live stream there. So what I'm going to do here is I'm going to tell my different computers to all work out different parts of the digits of pi. Actually, that's not going to work very well. Oh, dear. Because in order to work out the algorithm it uses, in order to work out the 1,000,000th digit of pi, it's actually working out all the previous digits up to a point. What can we do here? I want to ask it to longest sequence of consecutive ones in a long binary number. Yeah, I can do that. The problem is that I have to have computed the number in well, here in this. Let's get the digits of pi, and let's get them base 10. That means they're going to be, so let's just get 10 digits of pi. There they are. And I'm just going to get just the digits here, 3, 1, 4, 1, 5, 9, 2, 6, et cetera, et cetera, et cetera. So let's get 100 digits of pi. There they are. One of the really weird things about the digits of pi is they look kind of random once you've generated them. So if we just count how many digits there are of each of ones, how many twos, how many et ceteras, we'll find out this is saying the number of threes is 12, the number of ones is 8. Let's do this for 10,000 digits. So what we'll see is that the number of threes is very similar to the number of ones, is very similar to the number of fours, and so on. We could make a bar chart that compares the number of that. So that's telling us the number of ones, the number of twos. Actually, I'll tell you what, let's do the following instead. Let's make a word cloud that just shows what the relative frequencies of the numbers. Okay, so that's accentuating the differences. It says fives are slightly leading over ones and leading over zeros in the first 10,000 digits. But not very, it won't be by very much. And if we take, I'll tell you what, let's do this. Let's make a pie chart of those, and that's going to show us, so those pie slices are all pretty much the same, and that corresponds to the different digits of pi here. So what we could do, we can say in our digits of pi, so this is our digits of pi. Let's take the first 10,000 digits of pi. So let's call that digits, and there are our first 10,000 digits. Okay, just computed the first 10,000 digits of pi. Now we might say, is there a run of ones in that first 10,000 digits of pi? Somebody's wanting them to the left. Okay, there we go. The runs of ones in those digits of pi. Well, let me just work out the digits of pi without printing them out, because it's kind of, well, here, I just close them up like that. So I can say sequence position, I think, and then I could say, let's say a run of 1, 1, 1, 1, 1. Let's see whether there are any of those. There are no runs of 5 ones in the first 10,000 digits of pi. Let's see if there's a run of 3 ones. Okay, so that tells me where is there a run of 3 ones in the first 10,000 digits of pi. So it's telling me there's a run between positions 154 to 156. It says 1, 1, 1. So if I go in there and I say, let's go in there here, and I say, let's go and take positions, let's say 150 through 170. It better be the case. Yep, there we go. There's the 1, 1, 1 that it told us was there. Okay, so let us use all my parallel computers to answer a few questions here. So let's have them compute. Let's have my computers report on the question of whether there are so we can say in the first 10,000 digits of pi, let's ask the question, is there a run okay, so what I'm going to do, I'm going to say, yes, I'm going to say for digits, okay, here we go. Yes, all right, so let me show you what I'm doing here. All right, so what I want to do is I'm going to make I'm going to ask it. There's a little bit of a weird construct here, but let me show you how it works. Okay, so what this is doing is it's saying, it's making a table of tables. Actually, it's making a table of tables. And the first thing here is it's saying, this is a single 1, 2 ones, 3 ones, a single 2, 3, 2 twos, 3 twos, etc. So for each of these, I'm going to want to know how many times does each of those sequences occur in the first 10,000 digits of pi. So my idea here is that I'm going to work out for each of these, I am going to say, sequence count. That tells me how many times it occurs. Of this, a table with I up to 10 And let's just do n up to, okay, so let's do this here. And we're going to run this, and we're going to see how long it takes. Okay, so this is giving us, oh, it was really quite fast. Okay, let me do a slightly slower one. Okay, so this is showing us in the first 10,000 digits of pi, how many times did 1 1 occur, how many times did 2 1s occur, a run of 2 runs, 3 runs, etc. And so by the time we get up to a run of how many is there, 7 1s, there weren't any of those runs in the first 10,000 digits of pi. Let's make it 100,000 digits of pi. Okay, so that was taking a little bit longer. It took 0.55 seconds to do that. Okay, so now let's say I want the answer for the first, I want it for the first million digits of pi, and I want to work it out for, well, actually, let's do the same computation, but let's now just say parallel table, and let's say absolute timing, because I just want to know how long, let's do this one. Let's do just this one for a second. Absolute timing tells us if we just measured it on a stopwatch, how long would it take, as opposed to how long did it take just running in the CPU of the computer. Okay, so let's now do the same thing, but let's do that using my whole setup of 100 computers. Okay, so we saw in this case, this was a bit faster. Instead of taking 0.55 seconds, it took 0.11 seconds here. If we, let's make this run, let's do it, ask it to do a little bit more work here. Let's go up to 10 here. Let's see how long that takes. Okay, so that actually took even less time. It took 0.09 seconds, even though this thing was doing a lot more work. And the reason it took took less time is that all those computers of mine were running doing the computation. Okay, let me show you something. If I really want to get fancy here, let's see, parallel kernel status. Let's see whether this works. Okay, so this is showing me, for all my different computers, it's showing me the actual, how much they're running. So it says all those computers are ready to run, nothing's happening on them. So if I run this, see what will happen. I should see the thing light up. Let's see what happens here. Oh, it's not, it ran too fast, so they barely had time to light up. Let me try running, let's try running 1,000,000 digits of pi, see whether we can get them to actually show that they're doing something here. Let's see, is this going to work? Still too fast, sorry. But this would normally give me an indication of what, which computers are actually spending time. This would tell me the amount of time spent on each computer is still really, really tiny here. But this, and so people are asking, when does it make sense to divide a computation across a lot of computers? Well, basically, it takes, if the computers have to send each other a lot of data, they have to tell each other a lot of stuff. It's like loading a web page. It takes a while to send all that data across a network to each of the computers. So if there's a lot of data to send, then it doesn't make sense to send it across to all these computers. The best case is you just tell them, here's a computation I want you to do. You don't have to say very much to tell them what computation you want, but then the actual computation takes a bunch of time in each computer, and that's where the time gets spent. That's a good case for running a lot of stuff in parallel. All right, I think we've advanced to too high a level of advancement here, and I think we should probably wrap up. If there are, I would really encourage people, if you're well, for kids and adults, I just want to give a pitch again for this little book that I wrote, which you can find online, and you can find actually you can not only read it online, but also it has exercises. Let's take an example here. I don't know, let's do colors and styles. It should have exercises down here, and you press that button and it says, let's see, answer and check your solution. So it has a it has something here where you can actually enter enter what you think the answer is. Let's see if I can get it right. Red, yellow, green, and then say, okay, we can test out what it does, and then you say check my solution here, and it hopefully will tell me, yes, I got the right answer to that. So this is a convenient thing to do. There's also, by the way, there's a MOOC version of this that has videos that go along with each of the chapters of the book. If you guys really get into this, I encourage you to check out a website called challenges.wolfram.com, and that has a bunch of different challenges for, let's see, these are some coding challenges. Okay, so there are questions like, given a linear keyboard of letters of the alphabet, how many letters in total does your finger have to jump over in order to type a given word? So it's asking you, it's saying, can you write a program that does something like that? So I want to just say that what I've been doing here is showing you sort of examples of how you can communicate with a computer to get it to do things for you. I've showed you mostly sort of computations that happen locally on your computer. I could have shown you things like how I can put up a web page that does something, those kinds of things. And maybe another time people are interested, we can do that. I can show you like how to create interactive web pages and things with this. But I thought I would do this kind of experiment, and I'd love to get feedback on how this worked while we're all stuck quarantined. Actually, I've got lots of things to do, but this is fun, and I think hopefully it's useful to people. To show a little bit about how you can kind of communicate with computers and get them to do interesting things for you. So if people are interested, let us know what kinds of things you might be interested in. I could talk a little bit about, I can give you a menu of possibilities. We could talk a little bit about sort of a little bit more about how computers work, as well as how you can tell computers to do things. We can talk a little bit about how you can create things like websites, and how you can get your computer to do that. Or a variety of other things. Please give us feedback. I mean, I think yesterday I really had a lot of fun doing a Q&A about science. I'd be happy to go and do more of that because I had a lot of fun, and I had fun today too. But yesterday was particularly fun for me. If you guys can come up with interesting questions, we can queue them up, and I can see what I can do with them. But anyway, should wrap up here. Thanks for coming. We will post these notebooks and encourage you to have a play around, and let us know how you get on. Thanks very much, and hope to see you all another time.